Up until now, all of our washer methods have been they've all had an axis of revolution of either the x or the y-axis, which made them kind of simple because all of the radii associated with the washers and the discs were just the functions. So the purpose of this video is to start rotating areas around axes other than the x and the y-axis. That's why it's called other axes of revolution, meaning other than the two main axes, and just see how that tweaks this volume calculating process. But before we do that, I'm going to review a vertical and a horizontal of one of each around the x and the y-axis. So this first shape is enclosed by the graphs of negative x cubed plus 3, that's this upside down parabola, and y equals e to the x, the exponential graph in orange. And another reason I wanted to do these is because they cross at unique points. They cross at x equals negative 1.677 and 0.834, which are not values you would find by hand. So this is completely a calculator question. And we would solve this with a calculator and do the integral and everything on the calculator. But this, all you needed to do for washer method was know where to start and stop integrating. So that's what I just said. Negative 1.677 is our lower limit, and 0.834 is our upper limit. If you're doing this on your calculator, that doesn't make it any more difficult than if these were nice whole numbers. And the two numbers I need to know are the big radius and the little radius. So the big radius goes from the axis, which is the x-axis, all the way to the upper graph. So that's just the equation of the parabola. So that's going to be negative x squared plus 3. That's the big radius, and that's going to get squared in the formula. And then the little radius is going to be the distance from the x-axis up to the orange graph. And that's just the equation, y equals e to the x. So all I need to do there is fill in e to the x. So these are ones like we've done. We fill in the big and little radius, we start and stop at the proper places, and this one we would type into the calculator to get the volume. Okay, now this shape is contained in within the graphs of the square root of x, which is the red graph, and x cubed, which is the blue graph, and we're going to spin this one around the y-axis. Okay, so we had to tweak our process slightly if it was a y-axis axis of revolution, because the washer that we were forming now is what I'd call a horizontal washer. It's got this empty space in the middle, but it looks kind of like this. All right, but everything's in terms of y once we change over. If you're working with a horizontal rectangle, everything's in terms of y, and that's never going to change no matter what kind of volumes we find. So this one, I've got the limits of integration on this one are simple. This is probably one we could do by hand. This is going to go from 0 to 1, and that happens in both directions, but just to make sure you know, that's this 0 to this 1. That's vertical 0 to 1. The big radius is the distance from the y-axis to the blue graph, and the little radius is the distance from the y-axis to the red graph. And both of those distances could be called x, since they're horizontal distances, but because we are in y land, everything has to be in terms of y. So the big radius is the cube root of y, because if we take the equation of y equals x cubed and solve it for x, that's cube rooting both sides. And the little radius is x squared for the same reason. If you take the red equation and square both sides, you get x equals, I wrote and said x squared, I meant to say y squared. Y squared, because everything's in terms of y, and if you solve this other equation for x, you get y squared. So that's a review of a y-axis disk method, but it still was rather easy because the axis of revolution was the y-axis. So let's change that up. All right, we're going to go back to this first picture and recalculate this volume, but rotate it around some different axes. So on the top question, I'm going to rotate it around y equals negative 1. So that's down here. If I spin this area around y equals negative 1, I just create a different three-dimensional shape. It has a bigger empty space in the middle, but nothing's really changed as far as the washer method goes. I still want to keep these characteristics of the washer method. A pi on the outside. I'm still integrating from left to right from negative 1.677 to 0.834. That's not changing. I still have a big radius squared minus a little radius squared, and I'm still going to have a dx on the end. All right. Any problem with a vertical rectangle that is being spun is a dx problem. Every number and every letter you write is an x value. So now the only difference is what's the big and what's the little radius. So the big radius goes from the axis of revolution to the far edge of the shape. And that's going to be this green distance right here. The only difference between what we're doing right now and what we did on the review problem at the beginning is this green distance is 1 unit longer than it was originally. Originally we just called it the function negative x squared plus 3. Now it's going to be negative x squared plus 4 because it is this 1 unit longer than it was before. Everything else will be taken care of by the integration process in the calculator. Let's look at the little radius. This is the little radius. It goes from the axis of revolution up to the orange graph, the graph of e to the x. So how long is that? Well, if it were just the portion from the x-axis up, it would have been e to the x, but we're adding 1 to that, e to the x plus 1. Okay, this is, and at this point we are completely relying on the calculator. This is not something you're going to need to integrate by hand. You should know that immediately based on just the limits of integration. And don't try to simplify something if you're just going to type it in the calculator anyway. Just type it in the calculator as is. Make sure you get your parentheses right, and make sure you multiply by pi, and you're going to get your volume. All right, and to put one more twist on it, let's rotate this same area around y equals 4. So we're going to rotate it upwards around this line that's up above the shape. All right, and that just involves us renaming our distances again. Not a big deal. So let's set up what's true every time. We have a pi. In this case, we still have the same x values for our limits of integration. We have a big radius that we need to figure out squared. We have a little radius that's going to be squared, and it's still going to be dx. The only two questions is what are these radii if the axis of revolution is up here at the top of the graph going around y equals 4. All right, we're spinning up there. All right, so let's label them. Let's just look at them. Here's your big radius. It's going to go from the axis of revolution to the far edge of the shape. The little radius is going to be right here in purple. Now, since we're spinning it around y equals 4, these distances have something to do with the number 4. And what that is this. This distance between the x-axis and y equals 4 is 4 always. That's a consistent distance of 4. On the last problem, we added 1. If you're above, you're going to have to do some subtraction. So this red line right here, my big radius, is that 4 minus this distance right here, which is from the x-axis up to the orange graph, which is just e to the x. That's why we've been practicing naming these distances. So would you agree, hopefully you will, that this light red, this pinkish arrow, which is the big radius, is 4 minus the orange function, or 4 minus e to the x. Okay, that expression is going to give me the big radius no matter where I go from left to right across this area. Okay, so can you name the little radius? Try to pause for a second and name the little radius. That's that purple distance right up here. Okay, it again has to have something to do with 4 because it stops at a height of 4. So that purple distance is 4 minus this, and this is the other function. So this is going to be 4 minus the function graphed in black, negative x squared plus 3. So if you are rotating it around a line below the shape, you're going to add 1 to the graphs. That's how we got to +4 here and +1 here. If you're rotating it above, you're going to take that quantity, that number, and subtract the equations from it. So that's how we do a washer method in dx land with 1 above and 1 below. And here's our final example. Again, I strongly suggest that you completely pause and try to find the integral that you would get the volume for rotating this shape around x equals 1. So here's my axis of revolution, x equals 1. I'm going to spin this thing to the left, and it's going to kind of form this 3D shape. It's kind of hard to draw, but you get the idea. We're spinning it, I think I said to the left, we're spinning it to the right, and we want to know what's the volume of the solid that we create. All right, so if we're spinning something horizontally, that means everything is shifted to y. It means the rectangle is now laying over on its side. It means that the washer that I create is going to look something like this. It's not my best 3D effort, but you get the idea. And we need to set up an integral expression for this volume. Here are the things that haven't changed. Pi, 0 to 1, and again that's vertical moving up from 0 to 1. Big radius and little radius. Let's do big radius in black. This distance right here is the big radius. It's the distance from the axis of revolution to the far edge of the shape. Okay, can you name that distance? That distance is 1 minus this distance right here, and that distance right there has 2 names. One of them is x, and one of them is y squared. So my black arrow, my big radius, has a distance of 1 minus x squared. 1 minus y squared. And since big radius needs to get squared, I need a square on the outside of the parentheses. Okay, that's 1 because there's a consistent length of 1 here, minus y squared because this little arrow right here is y squared. Okay, and similarly, my little radius is going to be 1 minus the cube root of y, because we have a consistent 1 all the way across, just like we did with the big radius, and this distance right here, right here, it has 2 possible names. It's either called x, which we can't use because we're in y world, or it is whatever x equals. And if you take this equation and you cube root both sides, x is the same thing as the cube root of y, which is why cube root of y went right there. And then integrate on your calculator. This one you probably could do by hand. It might be a pain, but it would be possible. Okay, so that's how we deal with shapes that are rotated around axes other than the x or the y axis.